Welcome, curious minds, to another deep dive. Today we're plunging headfirst into one of the most, mind-bending, revolutionary concepts in all of modern physics, the uncertainty principle.
It really is foundational, isn't it?
Absolutely. And it's not just some abstract formula, it's a cornerstone of quantum mechanics, a theory that just radically shifts our understanding from that familiar, predictable world of classical physics, where everything feels so certain.
Right. Classical mechanics gives you the sense that, in principle, you could know everything precisely.
Exactly. Imagine trying to know everything about a tiny particle, like an electron, at the exact same instant.
Yeah.
Classically, you'd think, sure, you could pinpoint its exact position and its exact momentum simultaneously.
Theoretically, yes.
But then quantum mechanics comes along and it says, nope, fundamentally impossible.
Mm-hmm.
The core idea, at least initially, for position and momentum, is this trade-off.
Right.
The more precisely you know one, the less precisely you can possibly know the other.
And that possibly is key. It's not just about our current technology.
Right? It's built into reality itself at that quantum level. This principle is, it's famously distinctive, really one of the defining features of quantum mechanics.
You hear it discussed all the time.
Yeah. If you've ever listened to physicists or philosophers arguing about quantum strangeness, the uncertainty principle, especially tied to the Copenhagen interpretation, Heisenberg and Bohr,
Yeah,
it's almost always central to the conversation.
definitely.
So our mission today is to really unpack what this uncertainty actually means. In all its different flavors, what does it limit? Is it really a principle or something else? We're going deep into the original thinking of Heisenberg and Bohr, using some great sources, especially the Stanford Encyclopedia of Philosophy.
And it's important to clarify something right away, I think. The word uncertainty itself, it isn't quite as simple as it sounds in everyday chat.
Right, I don't know.
Exactly. In physics, and particularly in quantum mechanics, uncertainty wears several different hats. It can mean a simple lack of knowledge an observer has that's sort of an epistemological uncertainty. Or it could be about the inherent experimental inaccuracy you get when you try to measure something, like the limits of your ruler.
Makes sense.
But it can also point to something deeper, like an ambiguity in the definition itself. Maybe position just isn't perfectly defined for that particle at that moment.
Ah, so it's not just about our knowledge, but about the property itself.
Potentially, yes. And then there's the idea of statistical spread. If you prepare many identical systems and measure them, you get a range of outcomes. The uncertainty can refer to the width of that spread.
So lack of knowledge, experimental limits, fuzzy definitions, statistical spread, quite a few meanings packed into one word.
Precisely. And adding to the fun, even the pioneers, Heisenberg and Bohr, used all sorts of different terms themselves.
Oh, really? Like what?
Well, you see words like inaccuracy, spread, imprecision, indefiniteness, indeterminateness, even latitude. It shows they were grappling with the concept, too.
Wow. So this deep dive into uncertainty is really about exploring this rich, multi-layered idea that's been debated for almost a century.
That's the plan. It's a fascinating journey.
Okay, let's unpack this. Let's go back to the beginning with Werner Heisenberg and his path to these famous relations. It all kicked off in 1927 with his big paper, Über den anschaulichen Inhalt der quantentheoretischen Kinematik und Mechanik.
Right, and that word Anschaulich, it's crucial.
Yeah, I was just about to say, it's famously tricky to translate properly into English. Literally, it's like visualizable, something you can picture.
Like a little solar system model of the atom?
Sort of, yeah.
Mm.
But it also carries this sense of being intelligible or intuitive. So translators have used physical content, perceptible content, perceptual content.
The struggle just to translate that one word tells you something about the conceptual shifts happening, doesn't it? What does it even mean to understand the quantum world?
Absolutely. And to really get the context, we need to jump back just a couple of years to 1925. Heisenberg had already cooked up matrix mechanics.
The first real mathematical framework for quantum theory.
Exactly. And his core idea was pretty radical. Only focus on what's in principle observable. Forget trying to draw pictures of atoms.
Which many physicists found deeply unsatisfying at the time.
I bet. So physical quantities like position and momentum weren't just numbers anymore. They became these mathematical things, operators acting on a Hilbert space.
Okay, for those of us maybe rusty on linear algebra, what's the gist of an operator here?
Think of it less like a variable holding a value and more like an instruction. It acts on the quantum state and tells you the possible outcomes if you try to measure something. It's about the action of measurement.
Got it. So less what it is and more what you get if you measure it.
Precisely. And crucially, the operators for position and momentum didn't play nicely together. They had this weird canonical commutation rule.
Meaning the order matters. Measuring position then momentum isn't the same as measuring momentum then position.
Exactly.
Okay.
BP times AB times BP. And that little mathematical quirk, that non-commutativity, was basically the mathematical seed of the uncertainty principle itself. It screamed, these two things are linked in a weird way.
A quantum way.
Right. But then, just a year later, 1926, plot twist. Erwin Schrödinger enters with wave mechanics.
A completely different picture.
Totally different. He suggested electrons weren't just particles doing weird jumps, but maybe they were like oscillating charge clouds, evolving smoothly according to a wave equation.
Continuous, causal, much more classical feeling.
And here's the kicker. Schrödinger claimed his theory was Anschaulich.
Back to that word. But he meant it in the classical sense, right? Visualizable, continuous processes in space-time.
Exactly. And many physicists breathed a sigh of relief. This felt more intuitive, more like the physics they knew compared to Heisenberg's abstract matrices.
Which brings us to the question, why was Heisenberg so unhappy about this? You'd think competition would be good, but he was apparently furious.
He really was. Schrödinger's Anschaulich was exactly what many physicists wanted, that comfortable, continuous picture. But Heisenberg saw it as a step backward, a return to classical thinking that just didn't fit the quantum data. He famously wrote to Pauli, calling Schrödinger's Anschaulichkeit mist.
Which translates roughly as...
Well, various options depending on how much anger you want to convey. Junk, rubbish, crap, poppycock. Maybe even bullshit captures the strength of his feeling.
So he really hated it.
He did. He admitted his matrix mechanics lacked that classical visualizability, sure. But he didn't see that as a bug, more like a feature of reality. He thought they still lacked some essential feature in our image of the structure of matter, and his 1927 paper was his attempt to provide that missing piece.
So he wasn't rejecting intuition. He was trying to redefine what intuition means in the quantum world, adapting our minds to reality and not the other way around.
Precisely. He was saying, look, the quantum world is weird, our intuition needs to catch up. And here's where it gets really fascinating. Heisenberg's argument itself. He basically redefined Anschaulichkeit for quantum mechanics. For him, it meant you could grasp the experimental consequences qualitatively and see that the theory does not lead to any contradictions in simple cases.
So not about a mental picture, but about coherence with experiments and internal logic.
Exactly. And to make this work, he adopted this really radical assumption, his measurement meaning principle.
Okay, what's that?
The idea that terms like the position of a particle only mean something if you can specify an experiment to measure it. And crucially, any real experiment has inaccuracies.
So the meaning itself is tied to the achievable precision of measurement.
Yes. The meaning is only defined up to the unavoidable inaccuracy. It's a huge shift. Properties aren't just there. They're defined by the act of measuring them.
That is radical. How did he illustrate this?
With his famous thought experiment, the gamma ray microscope. Imagine trying to pinpoint an electron's position using a microscope.
Okay.
To get high accuracy, you need light with a very short wavelength, like gamma rays.
High-energy photons.
Right. But here's the quantum catch. The Compton effect. That high-energy photon hitting the electron isn't a gentle tap. It's a collision. It makes the electron recoil.
Disturbing its momentum.
Exactly. And the shorter the wavelength you use for better position accuracy, the bigger the photon's energy and the bigger the unpredictable kick to the electron's momentum.
So there's the trade-off, clear as day.
Yep. His first qualitative statement was basically, the more precisely the position is determined, the less precisely the momentum is known. And conversely, he estimated the product of these imprecisions, delta and delta Q, was about delta Q CMH, Planck's constant.
And he saw this coming directly out of that commutation relation, PDPQ, I/.
He did. He felt it was the direct Anschaulich content of that rule. He also tried extending it to time and energy, delta T, delta E SAM H, and action and angle, though those were trickier, especially time.
Time in quantum mechanics is always a bit special, isn't it?
It is. But the key shift in emphasis was this. It wasn't just a limit on what we can know. Due to the measurement meaning principle, it became a limit on the very definition of these concepts simultaneously. If no experiment allows perfect simultaneous measurement, then the concepts themselves aren't simultaneously perfectly defined.
That's a profound philosophical leap from epistemology to ontology, almost.
Absolutely.
But Heisenberg's argument wasn't static, was it? Bohr had some input, I believe.
He did indeed. Bohr, his mentor and colleague, offered some crucial critiques. Bohr pointed out a subtlety Heisenberg might have initially glossed over.
Which was?
It wasn't just that the momentum changed during the position measurement. The deeper point was that the amount of that change couldn't be precisely determined in the same experiment where you were measuring the position.
Ah, okay, so it's not just a disturbance, but an unknowable disturbance within that specific context.
Exactly. It highlighted a fundamental limit on simultaneous knowledge or definition, not just a clumsy pick.
And Heisenberg took this on board. He did. He refined his argument for his 1930 Chicago lectures. He stuck with the microscope. Accuracy delta q sim frec lambda, but the photon recoil gives an uncertain momentum kick, delta p sim frec lambda. Multiply them, and you still get delta p sim frec qh. The trade-off remains.
Okay.
But to tackle that measurement meaning issue more directly, he imagined a sequence. First, measure initial momentum precisely, small. Then measure position. Then measure the final momentum, again precisely.
All individually possible.
Right. But the crucial part is the change in momentum during the position measurement is unpredictable. You can measure the before and after momentum precisely, but you can't predict the change caused by the intermediate position measurement.
So you can measure the change after the fact, but you couldn't have known it beforehand.
Exactly. As he put it, it is, however, always possible to measure the size of this change in a subsequent measurement. You can retrospectively know the disturbance, but you couldn't predict it.
Okay, that's a subtle but important refinement.
And it led to a fascinating consequence. Heisenberg conceded that the uncertainty relation does not hold for the past.
Meaning?
Once you've measured something, its value is known, its history. It's no longer uncertain in the predictive sense. You could even, in principle, calculate the precise path before the measurement where delta Q might seem smaller than the limit. The principle is about predicting the future or defining the present, not reconstructing the past.
Wow, okay. That really clarifies its scope.
And this line of thinking pushed him towards something even deeper, the measurement creation principle.
Measurement creates reality.
In a sense, yes. He famously wrote, "The path comes into being only because we observe it." It wasn't just about limits on knowledge, it was ontological. Measurement forces the system to adopt a definite value. Before you measure position, it doesn't have a definite classical position. It's fuzzy. Measurement snaps it into focus.
So measure momentum, it becomes real. Then measure position, it becomes real, but the momentum has now changed unpredictably.
Precisely. Before that final momentum check, the electron has, in his view, a genuinely unsharp or fuzzy momentum. Ontologically fuzzy, not just unknown.
And he rejected hidden variables. The idea that particles do have precise values we just can't see.
Vehemently. He called that unfruitful and meaningless speculation. Physics, for him, was about describing observable data. Talk of an underlying, unobservable reality was pointless metaphysics. He warned against using words like reality or actually without empirical grounding.
Strong stuff. Very operationalist.
Very.
So where does this leave us? Heisenberg's ideas became central to the Copenhagen interpretation, but clearly their meaning is complex. Are these relations limiting experiments? Limiting concepts? Or denying simultaneous reality?
For Heisenberg, they were all intertwined, different facets of the same quantum truth stemming from his measurement meaning and measurement creation ideas. Limits on experiments, knowledge, and reality were inseparable for him. But, crucially, if you don't buy into his strict operationalism, other interpretations are possible. You could accept the relations as statistical facts about quantum states without accepting the full ontological baggage.
And since there's no single agreed-upon interpretation of quantum mechanics?
There's no single agreed-upon interpretation of the uncertainty relations either. It's still debated.
Which brings up the terminology itself. You mentioned Heisenberg didn't really call it a principle.
That's right. He usually said inaccuracy relations or indeterminacy relations. It seems Arthur Eddington, the British astrophysicist, might have been the first to popularize principle of indeterminacy around 1928, and uncertainty principle stuck in English.
Interesting, and Karl Popper argued against calling it a principle at all.
Yeah, his point was philosophical. A principle should be a foundational starting point, an axiom. but the uncertainty relations can be derived mathematically from the core postulates of quantum mechanics, specifically from the commutation relation. You can't derive the whole theory from the uncertainty relation.
So it's a consequence, not a foundation, in that view.
According to Popper, yes. But we can also think about Einstein's distinction between constructive theories and principal theories.
Okay, refresh my memory on that.
Constructive theories like kinetic theory postulate underlying entities, atoms, molecules, and build up explanations from their behavior.
Right, building blocks.
Principal theories like thermodynamics or special relativity start with broad empirical principles, things observed to be true, like the impossibility of perpetual motion or the constancy of the speed of light. These principles then constrain the form of the theory.
Got it. So where did Heisenberg see his relations fitting in?
It seems he likely viewed them as an empirical principle, a general law of nature forced on us by experiments, even if idealized ones like the microscope. He wanted to deduce quantum mechanics from these Anschaulich foundations, essentially from the uncertainty relation itself.
So closer to Einstein's principal theory idea, even if Popper disagreed on the term.
It appears so, yes. Though, ironically, the direct experimental verification of the relations being pushed to their limits only came much, much later.
Really? Not in the 20s or 30s?
Not with high precision. His arguments were based on those brilliant thought experiments. Real confirmation, like with neutron interferometry or manipulating single molecules, came decades later in the 80s and even the 2000s.
Wow. And you mentioned Heisenberg later shifted his view slightly.
Yes, apparently influenced by Einstein, he later acknowledged that it is the theory which decides what one can observe, giving a bit more weight to the theoretical framework itself in defining what's possible, rather than pure experience dictating the theory. A subtle but significant shift.
Fascinating. Okay, so if Heisenberg's initial formulation was qualitative, how did it get mathematically precise?
Well, Heisenberg himself was a bit vague on the exact definition of his delta Q and delta P, calling them something like the mean error.
Which suggests a statistical spread.
Right. And the first person to nail down a mathematically exact version was Earl Kennard in 1927, very shortly after Heisenberg's paper.
What did Kennard show?
He proved a theorem. For any quantum state, the product of the standard deviations of position and momentum must be greater than or equal to /2.
Okay, so he formalized uncertainty as standard deviation, a specific statistical measure of spread.
Exactly. And then Howard Robertson generalized this in 1929 for any two observables, say C's. Their standard deviations are linked by their commutator.
Delta, so if the commutator is non-zero, like for position and momentum, you get a lower bound on the product of spreads.
Precisely. If they commute, the lower bound is 0, meaning they can be known simultaneously.
Now, crucially, these are theorems, right? Derived from the math of quantum mechanics.
Yes, absolutely. They presuppose the quantum formalism, especially the commutation relations. They show the formalism is internally consistent with the idea of uncertainty rather than being empirical principles themselves. It's a consistency check, in a way.
But using standard deviation, that has some potential issues, doesn't it? You mentioned it connects awkwardly to the idea of measurement inaccuracy.
Right. Standard deviation is very sensitive to the tails of a probability distribution, those rare, far-out results.
So a state could have most of its probability tightly packed for both position and momentum, but a tiny possibility of a weird outcome could blow up the standard deviation.
Exactly. It might look very uncertain according to the Kennard relation, even if intuitively the particle is pretty well localized in both respects for most practical purposes. So standard deviation doesn't perfectly capture that intuitive sense of bulk localization.
I see. And you also mentioned applying these to time energy and other pairs wasn't straightforward.
No, especially time energy. There isn't generally a nice self-adjoint operator for time in the same way there is for position or momentum, which makes applying the Robertson inequality directly problematic. The status and formulation of the time-energy uncertainty relation is a whole complex topic in itself.
Okay, so the math brought precision, but also highlighted new complexities and potential mismatches with the original intuition.
That's a good way to put it.
All right, let's shift gears now to Niels Bohr. His name is always linked with Heisenberg and Copenhagen, but you hinted their views were quite different.
Very different in many fundamental ways. Bohr's starting point wasn't really the measurement problem, but the deep puzzle of wave-particle duality.
The fact that things like electrons and photons sometimes act like waves, sometimes like particles.
Exactly. Experiments force both pictures on physicists, but classically they're mutually exclusive. A localized particle versus an extended wave. How can something be both?
It's the core paradox.
And Bohr's radical step was his concept of complementarity.
Okay, what did he mean by that?
He insisted that elements from both pictures, wave and particle, were essential for a complete description. But, and this is the crucial part, he said these pictures don't refer literally to the underlying reality in a direct way.
So the electron isn't really a wave or really particle.
In Bohr's view, its nature, or rather the description that applies, depends entirely on the experimental context. What kind of question are you asking with your apparatus? Are you setting it up to see wave behavior, like interference, or particle behavior, like a click in a detector? You can't see both simultaneously.
So the experiment determines which complementary aspect manifests itself.
Precisely. And he criticized Heisenberg's initial focus on discontinuous changes occurring during measurement, like the photon kick. Bohr thought the uncertainty arose more fundamentally from the impossibility of simultaneously defining complementary properties like position, particle-like, and momentum related to wavelength, wave-like.
Because the experimental setups needed are mutually exclusive.
Yes. It wasn't just about an unknown disturbance for Bohr, but a deeper limitation on definition imposed by the experimental conditions required to give those terms meaning.
He had some key philosophical ideas underpinning this, right? Like about language.
Absolutely. Bohr stressed the importance of language. Physics ultimately has to communicate results unambiguously, and that requires extending ordinary language, supplemented with classical physics terms.
Why classical terms?
Because, he argued, our descriptions of experiments, the apparatus, the settings, the results, have to be stated in objective, communicable, classical terms. He called the whole setup and result a phenomenon, an indivisible whole involving the object, the apparatus, and their interaction.
Indivisible. Because of the quantum of action.
Exactly. His quantum postulate stated that any interaction involves an indivisible quantum, Planck's constant h. This means the interaction between object and apparatus can't be ignored or made arbitrarily small, unlike in classical physics. It's a fundamental chunk of interaction.
And this led to the buffer postulate.
Right. The idea that the description of the experimental setup must remain classical. The quantum weirdness doesn't infect our description of the laboratory equipment. It acts as a buffer, allowing us to talk about results even if the underlying process is unanalyzable classically.
So because the interaction is quantum and unanalyzable, and the setups for measuring complementary properties are mutually exclusive.
You simply cannot combine descriptions like precise position and precise momentum into a single classical picture. They are complementary, you need both views for a full account, but you can only access one at a time experimentally.
Can you give his example for position and momentum?
Sure. To measure position precisely, your measuring rod needs to be rigidly fixed to a reference frame.
Oh, yeah.
But if it's rigid, you can't track any momentum exchange between the object and the rod. So you lose momentum information.
Makes sense.
Conversely, to measure momentum precisely, using conservation laws, your measuring device needs to be movable, able to recoil.
Like weighing something on a spring scale.
Kind of. But if it's movable, it can't simultaneously define a precise position relative to the fixed frame. An instrument can't be both rigidly fixed and freely movable in the same experiment.
So the experiments are mutually exclusive.
And because the quantum interaction is unanalyzable, you can't neatly separate the object's properties from the interaction required to measure them. The classical ideal of a causal description, where everything evolves predictably from precise initial conditions, breaks down.
So complementarity was, for Bohr, a generalization of causality.
He called it a rational generalization of the very ideal of causality. We have to accept these complementary descriptions instead. His focus was always on conceptual clarity, using classical language for observations. The math, for him, was secondary, a symbolic representation.
That's a very different emphasis from Heisenberg's focus on the math and operational definition.
Radically different, yeah.
So how did Bohr specifically derive or view the uncertainty relations, the quantitative part?
In his 1928 Kumo lecture, he offered his own derivation. He started from the basic wave-particle links and bashed anew.
Connecting energy momentum with frequency wavelength.
Right. Then he used Fourier analysis. The idea is that to create a wave packet that's localized in space, delta x, and time, delta t, you need to combine waves with a range of wave numbers and frequencies.
Like making a short sound burst requires a mix of frequencies.
Exactly. Fourier analysis shows delta x delta sigma approx 1. Then, using the wave-particle relations, you immediately get delta x delta p approx h and delta t delta e approx h.
Ah, deriving it from the wave nature directly.
Yes. And his interpretation was key. These relations express the highest possible accuracy in the definition of the energy and momentum.
Definition, not disturbance.
Right. He explicitly avoided talking about discontinuous changes as the cause. For him, it stemmed from the impossibility of simultaneous definition due to complementary experimental requirements. He found Heisenberg's measurement creates reality language confusing.
He also didn't like purely epistemological takes, just about our lack of knowledge.
No. He felt saying, "we cannot know," avoids the deeper issue of whether these quantities are simultaneously real in a classical sense, which he tied back to the mutually exclusive conditions needed to even define them using classical concepts like space-time coordinates versus conservation laws.
So for Bohr, the uncertainty relations are fundamentally an expression of complementarity.
First and foremost, yes. Complementarity is the qualitative core. The relations provide the quantitative limits. They allow for intermediate fuzzy states, but Bohr mostly stuck to the need for classical descriptions at the observational level.
And his derivation using Fourier analysis handled time and energy more symmetrically than the operator approach.
It seems so because in his framework, time and space are often treated as classical parameters describing the experimental setup, not operators themselves, sidestepping the tricky time operator problem.
Okay, so we have Heisenberg's operational measurement focus view and Bohr's philosophical complementarity focus view, both leading to similar relations, but with very different interpretations.
Precisely. And understanding that difference is key to understanding the historical development and the ongoing debates.
Right. So after wrestling with these profound differences, let's step back to what's called a minimal interpretation. Why the need for that?
Well, partly because the deep philosophical commitments of Heisenberg, operationalism, measurement creation, and Bohr, complementarity, centrality of classical language, are, shall we say, not universally accepted today. Many find them too radical or perhaps unnecessary.
So seeking a less philosophically loaded view.
Kind of. The minimal interpretation focuses on what the quantum formalism itself directly tells us. In quantum mechanics, a system has a state, wave function. From that state, you calculate probability distributions for observables.
Like the chance of finding the electron here, or with that momentum?
Exactly. The operational meaning is if you prepare many systems in the same state and measure position on them, you'll get a distribution of results. If you measure momentum on another identical batch, you'll get another distribution.
No simultaneous measurements needed for this interpretation.
Correct. And under this view, uncertainty relations like canards, delta GQ, are just statements about the spreads of these probability distributions derived from the same state.
So it's about the properties of the quantum state itself.
Yes. It expresses the preparation uncertainty principle. You simply cannot prepare a quantum state where both the position distribution and the momentum distribution are arbitrarily narrow simultaneously. Canard's relation, Landau-Pollack, entropic relations, they all fit this preparation uncertainty idea.
But this minimal view leaves some things out, doesn't it? Like Heisenberg's original focus on measurement, inaccuracy, and disturbance.
It does. It doesn't directly address how accurate a single measurement is, or how much it disturbs the system, or the possibility of simultaneous measurements. Standard quantum mechanics simply doesn't have operators for simultaneous, perfectly accurate measurements of non-commuting variables like position and momentum. That impossibility comes from the structure of the theory itself, not directly from the standard deviation inequality.
So if you think inaccuracy and disturbance are core to the principle's meaning, the minimal interpretation isn't the whole story for you.
Exactly. Which leads us back to that question. If standard deviation has issues, are there better ways to quantify uncertainty, especially this preparation uncertainty?
You mentioned Landau-Pollack.
Right. Remember the critique of standard deviation being sensitive to tails. Landau and Pollack in 1961 proposed using bulk widths instead.
Which measures?
The width of the smallest interval containing a chosen fraction alpha, say 90% of the total probability, it focuses on where the probability mostly is.
Ignoring the weird outliers.
Pretty much. And their inequality gives a lower bound on the product that depends on the fractions in alpha and beta. It's less sensitive to tails and provides constraints not captured by the standard Canard relation. It's arguably a tighter, more intuitive bound on the state's inherent fuzziness.
Okay, that sounds useful. And the other alternative was entropic uncertainty.
Yes, using Shannon entropy from information theory. Entropy measures the unpredictability or spread of a distribution. Higher entropy means more spread out, lower means more peaked.
Like measuring information content?
Sort of, yeah. The entropic uncertainty relation gives a lower bound on the sum of the entropies for position and momentum, plus HBP-MAS sum, not a product. Right. And this relation is considered a strict improvement on Canard's, meaning it mathematically implies the standard deviation relation, but not vice versa. It also generalizes nicely to finite dimensions. It's a very powerful formulation.
So multiple ways to mathematically capture this inherent fuzziness of quantum states.
Definitely. Each with slightly different strengths and focuses.
Okay, now let's dive into that really active controversial area.
Yeah.
The measurement uncertainty principle. Trying to formalize Heisenberg's original idea about accuracy versus disturbance.
Yes, the idea that measuring position must disturb momentum and vice versa in a quantifiable trade-off.
The core claim being, you can't have a measurement procedure that's arbitrarily accurate for position and causes arbitrarily small disturbance to momentum simultaneously. There's always a trade-off.
That's the intuitive idea people have tried to formalize, leading to these error-disturbance relation debates.
And Ozawa kicked things off in 2003.
He did. He proposed formal definitions. Noise as basically the root mean square difference between the initial position and the measured value, and disturbance as the RMS difference between initial and final momentum.
Okay, seems plausible.
But his mathematical result was that the product of Flimbiki has no fundamental positive lower bound. It could, in principle, be zero for some setups. He claimed this violated Heisenberg's relation.
Violated? That sounds dramatic.
Yes.
But people objected.
Strongly. Critics argued his definitions didn't really capture Heisenberg's intuition. For instance, the operators involved don't commute, making the difference tricky to define. And you could find examples like just letting a particle drift, where Ozawa's error could be small with zero disturbance, which feels wrong.
So his math was right, but maybe his definitions didn't match the concept he was trying to capture.
That's the essence of the critique. It threw doubt on the appropriateness of his definitions for formalizing Heisenberg's specific microscope argument, not on the math itself.
Then came Bush, Lottie, and Werner, BLW, in 2013 with a different approach.
Yes, using a more modern formalism involving POVM's positive operator-valued measures, which can describe unsharp joint measurements. Since you can't measure P and Q sharply together, they looked at measurements that give fuzzy results for both.
Okay.
They then defined inaccuracy and disturbance by comparing the probability distributions from the unsharp measurement to the ideal sharp ones, using a sophisticated measure called the Wasserstein-2 distance. Crucially, they defined their final measures, and by taking the supremum over all possible input states.
Supremum, meaning the worst-case scenario for that device.
Exactly. It characterizes the device's overall performance, averaged over all possibilities, and their result was delta Fark.
Ah, so they did find a lower bound, a vindication of Heisenberg.
They certainly interpreted it that way. It's a powerful result, comparing whole distributions and giving a figure of merit for the device, like a microscope's resolving power.
But there was a catch, wasn't there? About the supremum?
Yes, a crucial one. Because they take the supremum twice, independently for error and disturbance, their relation tells you about the device's overall limitations, but it doesn't guarantee that for any specific state you measure, the product of the actual error and disturbance for that measurement will be above.
So it doesn't rule out getting lucky on a particular measurement and having both very small.
Exactly. It's a statement about the device's capabilities averaged over all states, not a state-dependent trade-off for every single run. So saying it fully vindicates Heisenberg's original intuition about a trade-off in every measurement might be stretching it a bit.
So no contradiction between Ozawa and BLW, just different questions being asked with different definitions.
Precisely. Ozawa showed his measures could be small for some states. BLW showed their different device-characterizing measures obey a limit overall. The debate is really about which definitions, if any, truly capture Heisenberg's original qualitative idea. And, well, the jury's still out on that. The final word hasn't been reached.
What a journey. We've gone from Heisenberg's first intuitive flashes and his battles over Anschaulichkeit through Bohr's deep philosophical concept of complementarity.
To the rigorous math of Kennard, Robertson, Landa-Pollack, and the entropic relations trying to pin down preparation uncertainty.
And finally into these really complex, ongoing modern debates about error disturbance and what it even means to talk about measurement uncertainty.
It really shows how this principle, which seems simple on the surface, is incredibly nuanced and rich.
Absolutely. It's so much more than just you can't know everything.
If you think about the bigger picture here, the fact that we're still debating the precise meaning and measurement of uncertainty for such a cornerstone concept, it really tells you something, doesn't it?
What does it tell you?
It tells me that our understanding of physics, of reality, is constantly evolving. Even bedrock principles get re-examined, refined, maybe even reshaped. And if physicists can debate the meaning of uncertainty this much, what does that imply about reality itself? Maybe the fuzziness isn't just out there in the quantum world, but also inherent in the act of observing and knowing.
A kind of uncertainty in the knower, not just the known.
Perhaps. It forces a certain humility about how fully we can grasp the world through observation alone.
We really have covered a lot today. Looking back over everything, what stands out most to you? Is it the philosophical depth of Bohr and Heisenberg's struggles, the cleverness of the mathematical formulations, or maybe this ongoing modern debate?
For me, it might be the enduring tension between the intuitive, qualitative picture Heisenberg started with the microscope, the disturbance and the difficulty of capturing that perfectly in the rigorous mathematical formalism. It shows the gap that can exist between physical intuition and mathematical precision.
That's a great point. And maybe a final thought for you, our listeners. Consider how this fundamental idea of limits, of trade-offs, might resonate beyond physics. Think about pursuing knowledge, understanding complex systems in your own life. Sometimes focusing intensely on one aspect inevitably obscures another. It's a powerful reminder, maybe, that clarity in one area can sometimes come at the cost of fuzziness elsewhere, something to mull over.